Hi everybody, Dr. White here with more discussion of how to figure out if infinite series converge or diverge. Techniques we learn in this chapter can apply to any infinite series, whether or not it has all positive terms. First one is called the ratio test. Say you've got a sequence, an, and you just look at the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term. Call that limit rho, and then suppose that limit does exist, okay? If that limit is a number less than 1, then the sum of those ANs converges absolutely. If that number is bigger than 1, then the infinite series diverges. And if it's equal to 1, then we actually don't know. The series might converge, might diverge. If you want to find out, you'll have to use some other approach. Okay, so here's an example. Got this infinite series. Does it converge or diverge? Well, here's the general term. So we want to look at the limit of the absolute value of the n plus first term over the nth term. So to get the n plus first term, you just plug an n plus 1 wherever you used to see an n in the formula for the general term. Okay, and we get this on top. And on the bottom, we've got our an. We need to take the absolute value of all that and then take the limit. Now, this time, the stuff inside the absolute value sign, it's all positive stuff. So it's its own absolute value. You don't need those absolute value signs anymore. We've got a ratio of fractions, fraction on the top, fraction on the bottom. So that means we can simplify a little bit. The bottom of the top fraction ends up on the bottom. The bottom of the bottom fraction ends up on the top. And the tops end up same places. Top of the top is at the top, top of the bottom is at the bottom. Looks like there's a lot of cancellation here. This cancels to just a 3, whereas this cancels to just a 5 on the bottom. So when I'm looking at the limit, I can just pull that constant outside the limit sign and look at n plus 1 over n. So that's another polynomial over polynomial problem. As n goes to infinity, I'm just going to divide the top and the bottom by n, and I get a limit I can easily process. That's going to be a 1. So 3/5 times it is 3/5. Okay, so the row number here turned out to be 3/5, which is less than 1. And so this infinite series up here, this one here, converges absolutely. So therefore it converges. And so we've answered our original question. So what's going on with the ratio test? Why does it work? Well, thinking about that limit, rho, well, it's what the an plus 1 over the an is getting closer and closer to, as n gets bigger and bigger and bigger. And so when n is large, the an plus 1, which is this term, would have to be approximately the rho times an. I mean, if the an plus 1 over the n is about rho when n is big, then an plus 1 must be the rho times an. Okay, so it's just approximate. This is just approximately 3/5 of an. Okay, so 3/5 of the previous, term. So when you think about your infinite series, the sum of all of the ANs, well, you can go out some way until you've got to some really large value of little n, like maybe capital M there. So that's like a lot of terms. And say after that point, the an plus 1 over the an is just so close to 3/5 that you might as well just consider it to be roughly 3/5. And so for the rest of the infinite series, the sum from capital M plus 1 to infinity, you can think that way. Okay, so I've broken the whole infinite series up into a part where the n plus first is not that close to 3/5 of the nth, and a part where it is really, really close. Okay. Now, thinking about this part, okay, it starts with am plus 1, right? Because that's where the n starts here. Now, thinking about am plus 1, that's about 3/5 of am. Next, it's going to have an am plus 2. Now, that's about 3/5 of am plus 1. So that's 3/5 of 3/5 of am, or 3/5 squared of am. A sub capital M plus 3 would turn out to be about 3/5 cubed times am. And it goes on like that. So this series here is approximately this series here. Here I'm summing k goes from 1 to infinity of am 3/5 to the, and that should be a k right here. I will make that change. Okay. So when we look at the whole thing, the whole infinite series, it's this sum here, which might be the sum of a lot of things, but it's still some finite thing, some finite number. And then there's the rest, which is this geometric series with a ratio r of 3/5, and that geometric series therefore has to converge. And so you'll have, a finite number in front, and then a finite number for the tail end of that infinite series. Finite plus finite is still finite. The whole infinite series has to add up to some finite number. It has to converge. So the idea is that the ratio test is showing you that once you go far enough out in this infinite series, the terms just look like the terms of a geometric series with a ratio of 3/5. And since a geometric series with a ratio of 3/5 converges, then our infinite series ought to converge too. It won't converge to the same thing, but it ought to converge as well. Let's try another example. How about this infinite series here? So again, trying the ratio test, we look for the limit of the absolute value of the n plus first term over the nth. So if I look at this term and I put an n plus 1 wherever I used to see an n, I will get this. And then here's the nth term on the bottom. And when I look at this, all the terms are positive this time, so I can take away the absolute values. And I need to rearrange my factors according to what's in the numerator and what's in the denominator, and I eventually get this. And then there's some cancellation. This 3 to the 2n plus 1, which simplified to the 3 to the 2n plus 2, is going to cancel a lot with 3 to the 2n, leaving only 2 3's up on top right here. And this 5 to the n cancels a lot with this 5 to the n plus 1, leaving only a 5 in the denominator. And that is a 9/5, which I will just factor outside my limit problem. And I've got the limit of n squared over n plus 1 squared. But I can write n squared over n plus 1 squared as n divided by n plus 1 quantity squared. Okay, so I've got the limit of the square of something. That's the square of the limit of the thing. Because squaring is a continuous function. You can move the limit sign inside of it. So looking at that limit, in the usual way, I see that that is 1. And so my rho turns out to be 9/5 times 1, 9/5, bigger than 1. So according to the ratio test, this infinite series is going to diverge. What's going on under the hood is that this time its terms, once you go far enough out in the series, its terms resemble those of a geometric series with a ratio of 9/5. That's bigger than 1 in absolute value, so it diverges. How about this infinite series? Does it converge or diverge? Well, again, trying the ratio test, n plus first term over nth term. Now, this time the terms are not always positive, but when I take absolute values, the absolute value of minus 1 to the n plus 2 is just going to be a 1, because minus 1 to the n plus 2 is either a minus 1 or a 1, and the absolute value of that is 1. Same here, the absolute value of this is 1. So all I got to do is look at the rest of the stuff and rearrange it. The n plus 1 factorial will end up on the bottom. The n factorial down here ends up on the top. And similarly, there's a 3n plus 1 over 3 the n. Now, there's a fair amount of cancellation here. All the 3's go away except for one of the 3's on top. Now, for the bottom, watch closely. There's a lot of common factors between the top and the bottom, but you got to look carefully to see what they are. I'm going to look at the bigger factorial over here in the sidebar, n plus 1 factorial. By definition, that's n plus 1 times n minus 1 times all the way down to times 2 times 1. But when I look at that, I see that it's n plus 1 times n times all the numbers less than it, and that's n factorial. So n plus 1 factorial actually could factor as n plus 1 times n factorial. And so I do that over here in my limit problem. I factor the n plus 1 factorial that way. And then I see there's opportunity for more cancellation. And so I'm really looking at just the limit of 3 over n plus 1, which is 0. So this time, the row is again less than 1, so the series converges absolutely. And so again, it converges. This time under the hood, what's happening is that the terms of the series are going to 0 faster than any geometric series does. You know, it's like the ratio term is 0, you know, once you go far enough out. Every term is like tiny, almost 0 in comparison to the previous term. Okay. I said the ratio test does not apply when the row number turns out to be 1, and I want to show you why that's true. Look at this infinite series. We know that it diverges because it is a p-series with p less than or equal to 1. Hey, that's the harmonic series. But when you try the ratio test on it, and you work with this ratio, you get 1. Okay, so when the ratio is 1, it is possible that the series could diverge. We just saw one where it diverges. But now look at this infinite series. That one converges by the alternating series test. Okay, let me fix the width again. Okay, when we try the ratio test on it, work on the absolute values and everything, then we're left with the same limit of n over n plus 1, which is 1. So now we've got a row of 1, but this time the series we're working with converged. So when your row turns out to be 1, you just don't know. Do you have a convergent series or a divergent series? It could be either way. And that's why the ratio test does not really apply when the row turns out to be 1. Another useful test is the root test. So again, if you got a sequence an, look at the limit as n goes to infinity of the nth root of the absolute value of an. Call that number L and assume it exists. If it's less than 1, then the infinite series composed out of adding up the an's converges absolutely. If L is bigger than 1, that infinite series diverges. And if L is 1, again, the test does not apply. You'll have to try to think of something else. Let's try an example. How about this infinite series here? Does it converge or diverge? Let me fix the width again. Okay. Trying the root test, L is this limit here. Now, let me see. This stuff inside the absolute values is definitely a positive number for all n's, so I could just take the absolute values away. And the nth root of a thing is the same as raising the thing to the 1 over n power. And so I've got a number to a power, but then all of that's raised to another power. So by a property of exponents, that's going to be my number raised to the product of those two powers. And 2n times 1 over n makes a 2. So I've got the limit of something squared, and so that will be the square of the limit of my thing. And when I look at this, I find that the limit is 3/5. So I've got 3/5 squared, which is 9/25, and that is less than 1. So this series converges absolutely. So it converges. The idea of the root test is really very similar to the idea of the ratio test. You know, if the limit of the nth root of the a_n's is L, then for large n's, the nth root of the a_n is approximately L. And so the a_n is about L to the n. And so the sum of the a_n's would be like the sum of L to the n, okay? But that's a geometric series. And so it should behave how geometric series behaves. If the L is bigger than 1, diverge. If the L is less than 1, converge, you know? But again, it does fail when L is equal to 1. You can construct similar examples to show that. Rounding off this section, we've gotten now a few more strategies and tests for determining whether an infinite series converges or diverges. It's a good time to stop again and put them all together and practice with them. So your strategies break down into thinking about two special series that pop up a lot, the p-series and the geometric series. So knowing what works with them, know that p-series converge when the p is bigger than 1. They diverge when p is less than or equal to 1. And know for geometric series, they converge when the ratio term is less than 1 in absolute value, diverge otherwise. And then you got some tests. Nth term test for divergence. We've got the direct comparison and limit comparison tests. Just remember that your series needs to have all positive terms in order to use those tests. And then we got the ratio test and the root test in this section. And if your series is alternating, positive, negative, or the other way around, negative, positive, then you've got the alternating series test you can work on. There's also that useful fact off to the side that absolute convergence implies convergence. If a series converges absolutely, then it converges. Okay, so let's see how you could just practice like putting these strategies together or deciding in a good way what's the best thing to look at first. So let's give ourselves some converge or diverge problems for just a bunch of infinite series. And I won't necessarily like work the entire problem out in great detail, but I want to look far enough into the problem to where we're convinced that we know the best approach to the problem and even have some idea about how it might turn out. So what if you had this infinite series here, converge or diverge? I see things that look like geometric series pieces in there. So why don't we look for a way to write this as a couple of geometric series? I could break up the fractions, and then I could just add the 2 to the n over the 7 to the n's, and then add the 4 to the n over the 7 to the n's. And 2 to the n over 7 to the n is 2/7 to the n. And this can be rewritten as 4/7 to the n. So what I've got here is two geometric series added together, and in both of them, the ratio terms are less than 1 in absolute value. So these add to 2, these are two finite numbers that are being added. That's finite. This series is going to converge. This one here, the nth term test for divergence is often overlooked by people, but it really should be one of the first things that you think about. Don't get tangled up with trying like the ratio test or the root test. Anything fancy on this one, because just look at the terms themselves. it's pretty easy to find out what they converge to. They converge to a half, which is not 0. So right away, by the nth term test for divergence, we know that this series is going to diverge. How about this one here? So, again, just kind of thinking nth term test for divergence, probably one of the first things you'll want to think about is, hey, do I converge to something that's not 0, or do I not converge at all? When I look at that, I see that on the top I bounce around between -1 and 1, but on the bottom, n squared gets bigger and bigger and bigger, so I know that's converging to 0. So the nth term test for divergence does not apply here. But along the way, thinking about that, I did think about that fact that my sine of n is always between -1 and 1, because that's the way sine is. So its absolute value is always less than or equal to 1. So you might want to consider, and what I'm thinking here has to do with this little side fact here, that absolute convergence implies convergence. You might want to just consider looking at the sum of the absolute values of your terms. That comes to this. And then you can think, well, let's see, since sine of n and absolute value is less than or equal to 1, this general term here is less than or equal to 1 over n squared. So why not look at a direct comparison with this series? That's a p series that converges because p is bigger than 1. So our series, which is less, is going to converge too by direct comparison. How about this one? Again, just sort of thinking about nth term test for divergence. I won't bore you with it by bringing it up every time, but just thinking about it, n cubed grows fast, but it doesn't go to infinity near as fast as 5 to the n does. We've learned that. And so this ratio here is going to converge to 0. So the terms go to 0. Nth term test for divergence does not apply. But I'll tell you this, whenever you see a mix of powers, like this third power function, and exponentials, like this 5 to the n function, whenever you see such a mix, the ratio test is often going to help you. So look at the limit of the absolute value of the n plus first term over the nth term. I dropped the absolute values right away because I could see stuff was positive. Rearrange stuff and look for your limit. There's a ton of cancellation. You're left with just like a fifth, and you've got the cube of n plus 1 over n. We've seen n plus 1 over n goes to 1, and so the limit is going to be 1 cubed times a fifth, which is just a fifth. So in the ratio test, the ratio came out to be less than 1. We know that this series converges absolutely, so it converges. That one looks pretty unfamiliar. Try nth term test for divergence. You come up with nothing because the terms go to 0. If you try the ratio test, you'll, after a lot of work, you'll find a limit of 1. So that test fails. Root test, same thing. It's not an alternating series, so you can't really look at the alternating series test. You might be down to your comparison and limit comparison as a way to go. Let's think about limit comparison. Limit comparison can sometimes be more computations compared to direct comparison, but it's also a little easier to set up. When I look at this, well, there's just a 1 on top, but I can think of something simpler that's similar to the square root of n cubed minus n. The n cubed is by far the most important thing going on in n cubed minus n. Square root of n cubed would be n to the 3 halves on the bottom. I would try limit comparison with this p series here. This p series, that converges. I should say converges because the p is bigger than 1. Big typo there. So let me fix that. Converges because the p is bigger than 1. The p is 3/2. It's bigger than 1. Everybody got that? Converges because the p is bigger than 1. Here it is, 3/2. Who knows? Maybe I hadn't had my coffee yet. Well, anyway, so since this series converges, when you do your limit comparison, you know, if your limit of like this term divided by this term comes out to be a positive finite number, then the two series will behave the same, and then you'll get that this one converges. And that limit does turn out to be, actually turns out to be 1. Okay. I'm throwing this one up here just to remind you of don't get sidetracked, look for simple ways to rewrite things. N to the minus 0.8 may look unfamiliar, but it's 1 over n to the 0.8. So this whole thing is just a p series from the get-go. The p is a 0.8, which is less than or equal to 1, so this series diverges. Same thing here. Don't get sidetracked into anything necessarily fancy, because if you use the property of exponents, the terms are 4 times 4 to the negative 2n. And then the 4 to the negative 2n is 4 to the negative 2 to the n. 4 to the negative 2 is a 1/16th. And lo and behold, I'm looking at a geometric series where the ratio is 1/16th. That's less than 1 in absolute value. So this series will converge because it was just a geometric series slightly disguised. Now, that doesn't mean that you know, you're damned if you don't see that simple rewrite. Like what if you tried the ratio test? Which, after all, I'll tell you this: the ratio test is going to be really effective, quite often, really effective when you see just exponentials, you know, in your problem, like not exponentials and factorials and powers, but just exponentials like this. The ratio test is often going to be good and simple. So just look at the limit of the nth root of the absolute value of the nth term. So you're looking for this to the 1 over n to get the limit. Well, see, that would be the 4 to the product this times 1 over n. So I've got a minus 2n plus 1 over an n. So that's a minus 2 plus a 1 over n when I break up the fraction. And the 1 over n is going to 0, so this limit's got to go to 4 to negative 2, which is 1/16. That's less than 1. So we're kind of rediscovering the geometric series in our analysis with the root test. So no problem. And sorry, that was another typo there. Root test, not ratio test. That was a real need for me to get my coffee before I started writing those notes, huh? That should say root test. I'll correct it. I've got it corrected in the PDF that you will see. Okay. Try another one. This one's really scary looking. Sine of 1 over n squared. You know, so it's like, gee, 1 over n squared is familiar, but it's being hidden by sine. What in the heck can we do? Well, about the only thing we know about sine of x is that the limit as x goes to 0 of sine of x over x is 1, you know? So, you know, we're knowing that that limit is 1 and really not knowing much else, let's just go on the hope that they set us up a problem where that fact is going to be useful. So think about the limit as n goes to infinity of sine of 1 over n squared over 1 over n squared. You know, the 1 over n squared would be going to 0. So you're looking at this problem in disguise, you know. This limit is going to be 1. So I think you ought to be doing limit comparison with the sum of 1 over n squared. We've already found that the limit of the ratios of the terms is 1. So we know, because it's 1 is just a positive number, we know by the limit comparison test that the two series will behave the same. That's a convergent series because it's a p series with p bigger than 1. So this one's going to converge too. How about this one here? So There's a couple of things that could be done here. You might, well, no, I'll just say, I won't say might. I'll just say what occurs to me first, and that works just fine. I'm seeing a mix of powers, n to the 1/2, and exponentials, -2 to the n here. So the ratio test has proved helpful in situations like that before. Let's see what it does for us now. So I try to get my row, and I end up having to look at the limit of this. And it looks like there's like a 1 that somehow got smudged out. Is that missing in the original? Yeah, okay. I just forgot. I didn't put in the 1. There should be a, when we take the absolute value of -2 to the n plus 1, we get 2 to the n plus 1. There should be a 2 to the n plus 1 there. And then this is the 2 to the n that you see on the bottom. Okay, and so that's going to cancel a lot to just be a 2 on the top. And then this root n over root n plus 1 that you have to deal with is the square root of n over n plus 1. Well, the n over n plus 1 is going to 1. Square root of that is 1. So that times 2 is just headed to 2. Okay, so our row has turned out to be a number that's bigger than 1. So we know that this series is going to diverge. Here is one where there's just exponentials, something to the nth. So the root test, according to previous experience, the root test, might be very effective, and you might try that first. And so you give it a try, and you end up looking for the limit of this to the n to the 1 over n, terms to the 1 over n. And by property of exponents, that's just this to the n times 1 over n. So it's just the n over n plus 2. And that limit is 1. So the root test fails on us. It's not going to decide convergence or divergence. Actually, looking back at it again, and this can be tough to realize first few times around, this could be rewritten as this. Switch the n plus 2, the n over n plus 2 to n plus 2 over n, and you're doing 1 over. And if you break up that fraction, you're looking at a 1 plus 2 over n inside. So I'm looking at the limit of 1 over the limit of this. But you know what? We found with L'Hopital's rule that the limit of 1 plus r over n to the nth power, there is a missing to the nth power right here. There should be an nth power. So I've just corrected that. The limit of 1 plus r over n to the n is e to the r. I'm looking at the limit of 1 plus 2 over n to the n. So I'm going to get an e squared. So actually the terms of this series converge to 1 over e squared, which ain't 0. And so the series diverges by the nth term test for divergence. So that's pretty interesting. You keep this thing in mind and look for ways to write an expression so that it contains it, you can often get a lot of insight. One last question for you. Suppose we've got a sequence, an, and we find that the limit of the absolute value of the n plus first term over the nth term is a third, okay? Fix the width. What could you say about this infinite series here? So you're still not being told the an, but you're looking at this series. I guess that would be a 1 times a1. It would be a 2 cubed 8 times an. It would be a 3 cubed 27 times a3, and so on. What can you say about that series? Is it like converge absolutely, converge conditionally, diverge, what? Well, try the ratio test on it, and you'll be looking for this limit. And that'll take you to looking for this limit. Now, this part is going to 1/3. This part we've seen is going to 1 cubed, which is 1. So the row number in the ratio test is 1/3, is less than 1. This series is going to have to converge absolutely. What about 2 to the n times an? So again, try the ratio test, and you end up looking at this, which ends up converging to 2/3, which again is less than 1. So again, your series converges absolutely. How about like this, the sum of 3 to the n times an? This time you end up, when you do the n plus first term over the nth term and you rearrange, you end up with a 3 to the n plus 1 on the top and a 3 to the n on the bottom, just like you did here. And so you got a 3 times this, and you're taking the limit, but this goes to 1/3, so you're looking at 3 times a third, and you're looking at 1. And so this time you're not sure. The infinite series could, diverge. It could converge. We don't know. You might ask yourself, like, what if you put a 4 there instead of a 3? What would happen? That would be good practice. Okay, sorry for all the typos, but I am done with this section, so I'll see you later.